Yeah, good afternoon. Welcome to the session. This is Dr. Damodar Reddy, Department of EEE, Associate Professor. So, in this session, we are going to deal with these thyristors. So, when come to the introduction part, thyristors are one of the most important types of power semiconductor device. So, we can say thyristors are controlled devices. So why we are going to thyristors means it's a controlled device. So controlled device which are having many benefits in the power electronic converters. So they are operated as bistable switches operating from non-conducting state to conducting states. So initially this having three modes of operation, so that we will discuss in later. And thyristor can be assumed as ideal switches for many applications. So in reality thyristor exhibit certain characteristics and they have some limitations in this study. So conventional thyristors are designed without gate control turn off capability. So that can be overcome by using this thyristor concept, and the thyristor will turn off when the current is brought to 0. So there are many methods to turn off the thyristor. We can say line commutation and forced commutation. For making the thyristor off, we have two methods like line commutation and the second one is we can use the forced commutation. So these two are the methods. So we can use to turn off the SCR, and there are gate turn off thyristors in the thyristor family which will be controlled by gate current. So when come to the construction point of view, so thyristor is a 4-layer device. We can say here 4 layers in the thyristors like PNP thyristor it is. Let us think, if you see this, it's a 4-layer device, so which is having PN, PN. So like there are 3 junctions J1, J2, J3, and terminals are anode and cathode along with a controlled terminal, that is you can say gate. So this is a 4-layer 3-junction device and one control switch that is called a gate. So thyristor have lower unstate conduction losses and higher power handling capacity compared to the transistors. So because of the controlled state in the available in the thyristors, we can go with the thyristor concept other than the MOSFET or IGBT power transistor devices. So however, transistor have higher switching speed and lower switching losses. So when compared to the thyristor concept, this power semiconductor device like transistors having little benefits when while talking about higher switching speeds and switching losses. So this is the symbol of representation for thyristor, which is having 3 terminals: anode, cathode and gate. 3 terminals. So this is the controlled switch which is supplied by some other external supply, and this anode to cathode is given plus and minus, so from the main supply, and this one is the representation of construction of thyristors. So here you can see the anode, cathode and gate with 4 layers and 3 junctions in this structure, and this structure having 3 operating states. One is forward blocking state, Next one, reverse blocking state. Reverse blocking state and forward conduction state. So these three are the operating states in the thyristor: forward blocking state, reverse blocking state and forward conduction state. So what happens in the forward blocking state, we will see. So in the forward blocking state, the supply is given between the anode and cathode. That anode is positive with respect to cathode by the time J1 and J2 junctions are in the forward bias. So but the J2 junction is in the reverse bias. So there is no flow of current from anode to cathode because of this junction J2 in the reverse bias. So in order to increase the anode to cathode voltage, if you increase the anode to cathode voltage more than the breakover voltage, that is VBO, we can say breakover voltage or breakdown voltage, if you increase the voltage between the anode and cathode, so then at breakover voltage, that we can call it as avalanche breakdown happens at the junction J2. So that is one of the method to increase the anode to cathode voltage and making the thyristor, making the SCR into conduction state. So that means forward blocking state. So there is no conduction actually. If you increase the voltage from anode to cathode, it will become conduction. But this is not a feasible method to make the thyristor into on state. So the next one is reverse blocking state. So in this, in the reverse blocking state, what happens? Anode is negative with respect to the cathode. So there is a junction J2 and J1 and J3 are in the reverse bias and only J2 is in the forward bias. So by the time these two junctions will oppose the flow of current here, so you will not get any current in this case, but some leakage current will flow through the junctions. So that leakage current is nothing but reverse leakage current. In the same way, the current is flows through in the forward blocking state also, that forward leakage currents. These two states are in the off state condition of the thyristors. So let's move on to the forward conduction state. So here in this case, forward voltage is given between the anode to cathode, that means anode is positive with respect to cathode, then gate signal is applied here, then because of the gate signal the junction J2 will be breakdown at some particular voltage, that is called avalanche breakdown, or we can say breakover voltage. So therefore current will flow from anode to cathode in this case. So therefore the switch is coming from forward blocking state to forward conduction state. So these three are the modes of operation in thyristor. So this is about all the theory behind this blocking and forward and reverse conduction states. So how it will be happen, we will see with the diagram. So this is the basic diagram. So we can use for the explanation of thyristor characteristics. So here it is the main supply. Main supply is given between the anode and cathode. This anode is positive with respect to the cathode. Then there is a forward direction of the thyristor, but unless there is no gate signal, it will be in the forward blocking state. This is in a forward blocking state. So until VBO or breakover voltage, so this thyristor will be in the forward blocking state. So by varying the resistance value, we can keep the anode to cathode voltage to the VBO. And similarly, by closing the switch S, so we can give a gate current between the gate and cathode. So from the gate and cathode, this is positive with respect to the cathode is minus. So by varying the resistance positions, we can vary the additional source ES and the current will be supplied to the gate signal. Then there is a junction J2 will be breakdown, then therefore plus to minus, that is anode to cathode current will flow through the thyristor. Then that is a on state switch of the thyristor. So that we can observe here. So there are forward blocking state, forward current, forward leakage current. This is in the forward blocking state only. So we will get the some minor, due to the some minority charge carriers, we can have forward leakage current in this period. And during the reverse blocking state, so there is a leakage, reverse leakage current due to the minority charge carriers. So after the breakdown voltage in the reverse also, there is a sharp increase in the current, and this sharp increase in the current can damage the your thyristor switch. So it may damage the your SCR. So this is not a feasible method to apply reverse voltage between the anode and cathode. So the best way to operate the switch off states to on state is nothing but through the gate signal. So this is about operating the thyristor from forward blocking state to forward conduction state. And there are two important things here, latching current and holding current in the SCR. So as we keep on changing the current in this operation, so there is a Ig3, Ig2 and Ig1 are the gate currents varied for making the thyristors into on state. So the latching current is the minimum current to hold the thyristor into on state. After that the gate signal is removed, therefore the switch will be in the on state, and the holding current is the minimum anode current which will hold the thyristor into on state. So this is about holding and latching current in this state. So after some time, even if you remove the gate signal, there is a sharp increase in the current, anode to cathode current, because already the switch is into on state. So therefore the current will be increased very sharply, then it will be in the conduction state. So this is about one of the state when cathode voltage is positive with respect to the anode, the junction J1 and J3 are reverse biased and J2 is forward biased. So this is like two series connected diode reverse biased. So this is about theory behind the reverse blocking state. The reverse leakage current is known as reverse current IR. A thyristor can be turned on by increasing the forward voltage beyond the VBO, but such a turn on can destroy the thyristor. So that's what. So we cannot go with the maximum voltage. So we cannot go with the maximum VBO, breakover voltage, in the thyristor concept anode to cathode, because the gate signal is in the off state. So though we can turn on the SCR by applying anode to cathode voltage. So anode to cathode voltage, forward voltage we can increase. So in this forward voltage also we can turn on methods, but there is a damage of your switch. Similarly we cannot increase the reverse voltage also between the anode and cathode. So that is also a danger to the switch. So that may be damages. So in practice the forward voltage is maintained below VBO and the thyristor is turned on by applying positive voltage between the gate and cathode. This is the best way of doing your our experiment while working with the SCR. So keep some voltage between the anode and cathode, then we can give the supply to the gate and cathode, then there is a smooth operation of your thyristors from off state to on state, like forward blocking to forward conduction state. So that's what. Once the thyristor is turned on by gating signal, the device continue even if the gate signal is removed. This is nothing but your latching current. So that's why the device can be called as latching device. So once the gate signal is given to the thyristors and device is turned off, then the device get into on state. So even though there is a gate signal removal, it will be in the on state only. So this is about modes of operation of the thyristors. So the same can be explained by using the two transistor model of thyristors. So here the latching action can be demonstrated by using the two transistor model of theory here. So one PNP transistor and one NPN transistor coupled together. So this is the PNP transistor 1 and Q1, you can say this is the Q2 transistor, both are coupled connected together to make the transistor operation. That's what we can say. This is a two transistor analogy of the thyristors. So here it is a PNP transistor and NPN transistor, same the 3 junctions, it is having 4 layers and 3 junctions J1, J2, J3, and here anode to cathode voltage is applied to the Q1 and Q2, that is the forward voltage applied between the anode and cathode, and the base of the QT is supplied by the gate. That means the current IC1 and gate is applied to the IB2. So two currents will flow through this base IB2. So then your Q2 switch is turned on. So before that the forward voltage, so forward voltage is given to anode to cathodes, therefore Q1 get into on state and the Q2 base is controlled by this IC1 and IC. So here by making this also we can turn on the thyristor concept. So by making two transistor back to back connection, we can make the thyristor into operation. So the collector current IC of the thyristor is related to the emitter current IE. So and the leakage current of the collector base junction IBO. So we can write the equation in terms of collector current alpha into IE plus IBO. So this is the fundamental equation in any transistor. So where alpha is nothing but IC by IE. So therefore the current given to the Q2 through the IC1 and IC. So you can take the IC1 as IC1 is equal to alpha 1 IA plus ICBO 1. Similarly IC2, this is the collector 2 Q2 current, that alpha 2 into IK plus IBO 2. So from this we can say anode current combination of these two. So the anode current of the transistor analogy can be taken as the combination of sum of this IC1 and IC2. So both current can be taken IC1 plus IC2, that we have alpha 1 IA plus ICBO1 plus alpha 2 IK plus ICBO2. This is the anode current of the your thyristor switch. So but what is the cathode current here? The sum of anode and the combination, like, so where we have anode and cathode. So here it is a Q1 thyristor is there. So here it is anode and cathode is connected to the Q2 of base. So here it is a gate signal. So this is the cathode and this base is connected to this. So here the current flowing through the cathode is nothing but coming from the anode anode terminal to cathode and from the IC1. So this is nothing but sum of your anode current flowing through this switch and IG current given to the gate signal. So this is the anode current flowing through the your circuit. So therefore we can write the total current IA current, that is alpha 2 IG plus ICBO1 plus ICBO2 divided by 1 minus alpha 1 plus alpha 2. So this is the your total anode current flowing through the circuit. So the alpha varies with emitter current and the variation is shown in figure. So here it is. The alpha value is taken here in the y-axis and emitter current in this. So it's a change in the emitter current will show the alpha value. So that is nothing but if alpha 1 plus alpha 2 is tends to 1, then the denominator will approach to 0, then IC will be infinite. So then, so we have to adjust the alpha 1 and alpha 2 values to make the thyristor into on state. So therefore, consequently the thyristor will get into turn on. So this is how we are going to operate the 2 transistor model of SCR.